Thank you very much. It was a long paper, so I've tried to redact as much as possible and provide a concise presentation for this work. We published this paper approximately 6 months ago. So without further ado, I'll just dive in. We work with pMUTs. We use typically linear arrays as the one you see over here. And typically, each channel would correspond to a column of pMUTs that we will fire in different ways. And typically with a single column of pMUTs, you would get a very wide field of view, but you would have an issue with your the maximum output pressure that you can possibly attain. And that will have an implication on how large your conventional detection area would be. Now, if you wanted to enlarge that into more towards the mid-range, then one of the ways you can try to do it is that for each channel, you assign 2 columns of membranes. And that would be great because you will be able to extend your detectability. However, that could be at the cost of you narrowing down your field of view. And that will introduce different implications. Now, there would be also other ways to, on such a scenario, there would be other ways for you to try and improve the localization of your of the targets or the SNR. For example, you could try transmit focusing, or you could try more advanced image reconstruction algorithms that like delay, multiply, and sum. But that would not work theoretically very well because of the issue with the narrow field of view for your array. So this work effectively, starting from that concept of using narrow field of view pMUT arrays for immersion, they try to cover the gap of being able to do imaging at short range and mid range by introducing 2 novel algorithms. The first algorithm is effectively a calibration technique that intends to suppress the crosstalk and effectively enlarges the conventional detection range close to the array, so you can detect reflectors that are closer to the array. And the second innovation from this work is a novel image reconstruction algorithm, which is based in received signal multiplication, so a sort of delay, multiply, and sum approach, but with a twist, which is the localized coherence rule. Very quickly, I'll just go through the method for the crosstalk suppression. You see at the top of the slide the block diagram. For each signal, we first calculate the continuous wavelet transform, which is equation 1. That's effectively a measure of how similar a signal is with a delayed and scaled version of a mother wavelet. In this work, we selected the Morley wavelet. You see the real part of that plotted where my flash is. And effectively, that matches better the signal intricate characteristics like the distortion, the delays, the variability of the signal, and also the ring down. Effectively, the complex correlation coefficients from equation 1 can be plotted in a sort of periodogram, thinking of it from a time frequency analysis. But in our case, it's a 2D scalogram of time and scale. Now, the next step involves identifying the maximum value of the scalogram and then mapping the scale value, which is effectively taking the red line. And if we plot that, that's effectively what 1D scalogram and a function of time. In the next step, we find the analytical representation of that using equation 3. And given that that is a complex number, then we calculate the phase based on equation 4. Now, that point, we can plot the phase unwrapped continuously. And if we look at an example on the 2 plots over here, so it's effectively this plot, and then the below one is the zoom in. It's an example of a received signal in blue, which has a very, very tiny echo. It's a little bit grained because of the enlargement. And effectively, the phase is the purple line that goes all the way up. The next step will involve what's called here as tangent line calculation. And effectively, a linear model is fitted on the phase data in order to calculate this tangent line to the phase. And then the final step involves identifying when that tangent line is crossing through the x-axis. And we take that cutoff point and we set to 0 the early portion of the signal. And that enables us to effectively eliminate the crosstalk. Now, once we calibrate our data, process the data like that, then we need to calculate the signal envelope using Hilbert, and then we need to continue with the image reconstruction. Now, to do that, the proposed DAM, delay and multiply localized coherence rule methodology goes as follows. It's expressed by equation 5. But what does that mean? Let's look at the diagram over here on the right. So we redefine the received signals by starting from channel 2 and saying that I'm going to do a point-to-point multiplication as expressed by equation 5 from signals from channels 1, 2, and 3. So for the third channel, it will be 2, 3, and 4, and so on and so forth. And obviously, you see, we start with 2, we finish with the penultimate channel of the array, which means that channels 1 and channels 2, because they don't fit the rule, we exclude them completely. So it's as if we don't have data from channels 1 and the last one. And then we feed that data set to delay and sum. Similarly to the way we applied the localized coherence rule in the previous slide, we can also sort of apply it in the conventional delay, multiply, and sum algorithms. And we have delay, multiply, and sum of multiplications of two signals, which traditionally is expressed by equation 6. So effectively, it's multiplications of received signals across all the channels. And for having in mind the narrow field of view array, we need to eliminate that. And we do that by by expressing it with equation 7, which effectively says that for every channel, you only do multiplications of that signal from one pitch channel neighbors. So the one pitch on the left and the one pitch on the right, if there are one and two. And then for the first and the last channel, it's effectively a single multiplication. So channel 1 will only have channel 2, and the last channel will only have the penultimate channel. Similarly, again, for the delay, multiply, and sum, the equivalent implementation using the localized coherence rule is equation 8. In this case, we are effectively modifying the algorithm to consider received signal multiplications from channels at one pitch and pitch distance away. Now, to characterize the concepts, the methodology here, I deducted only 2 experiments. The original paper has 5 experiments, so I do recommend you having a look at it. So the first experiment is trying to shed light in what's happening to when we have the narrow field of view pMUT array, which is double columns per channel for an 18-channel pMUT array, whereas and compares it directly against an 18-channel pMUT array of the same design, but each channel is a single column. So the narrow field of view array and the wide field of view array for the scenario you see on the left-hand side over here. And the second scenario is effectively to try and see whether a narrow field of view pMUT array can actually achieve a lateral resolution of 1.5 millimeters. We immersed the array and the whole setup in a tank filled with fluorinated FC70, and we use Verasonics for the data acquisition and the actuation. And the pMUT array has a 6.5 megahertz resonance. There is more details, but in the paper, I think you guys can do it. Very quickly here, I just want to show how effective the crosstalk suppression algorithm is. As we say, we have here the original received signal, and we compare the method we developed here with a different method we have actually presented last year at Sensors, called sliding window autocorrelation. It's again a calibration method to suppress crosstalk, and that kind of like state-of-the-art algorithm actually results in us clipping off the first 2 centimeters, which is quite detrimental because it means that you cannot really detect a reflector which is within the first 2 centimeters from the face of the array. On the other hand, the proposed algorithm can actually illuminate the first 6.78 millimeters, which means that if a reflector is as close as 7 millimeters from the array, you can actually localize it. Now, in this slide, we see the results from comparison between the narrow field of view and the wide field of view from experiment 1. And on each row is first row double column, second row single column of pMUTs. And the first column of data is effectively results from COMSOL simulations of a single membrane and a double membrane measuring the normalized output pressure, where we actually demonstrate that a double column pMUT array has a very narrow field of view, 30 degrees, whereas a single column pMUT array has an almost 180 degrees field of view. So that's more to set the record about the field of view. And so looking at the double column array, we see that here we tried delay, multiply, and sum 3, the conventional way. And we see that, okay, we can kind of localize the reflector, but the reflector's dimension is not correctly reconstructed. There is a bit of an aliasing, with the reflector being shifted towards the right. It's supposed to be somewhere at the center between 0 and 2.5 millimeters, but it's not. Whereas when we apply the proposed methodology, the delay and multiply localized coherence rule algorithm, we can actually shift it back and give it the correct dimension of 3 millimeters. On the other hand, with a single column reflector, applying either algorithms will have sort of the same effect. It won't really change the kind of like the lateral representation of the reflector, as expected to an extent. So in this result, we benchmark performance for all of the image reconstruction algorithms, considering the narrow field of view pMUT array. And we have first row is the conventional algorithms, delay and sum, D-2, D-3, and the second row is the proposed methodology and the modified D-2 and D-3 with the localized coherence rule. Now, we see that the conventional methods for a narrow field of view array do not really enable the array to localize the two reflectors. There is a lot of reflector misrepresentation of the energy intensity, particularly at the extremities of the reflector. You see predominantly in the center of the two reflectors, there is a lot of energy diffusion, a lot of spreading of energy. It gets a little bit better as we move to more complex algorithms, but obviously applying delay, multiply, and sum for a narrow field of view array where there is not a lot of intersection in the coverage between channels will also be detrimental because it will cancel out a lot of the valid areas. So you see with delay, multiply, and sum 3, there is a lot of cancellation on the right of the one reflector and on the left of the other reflector. When we apply the localized coherence rule, we can effectively correct for all that. We eliminate the aliasing. We actually suppress very effectively all the background noise that you see in the original reconstructions. And the bottom line, I think, is the last bullet point here. So receive signal multiplication using the localized coherence rule can optimally relate the coverage of adjacent pMUT channels when we have an array with a narrow field of view. In this slide, I want to highlight one thing, and that is if you compare the proposed algorithm with delay and sum, we triple the SNR while keeping the computational cost the same. So it's very important that although the narrow field of view array can give a very good localization with a lateral resolution of 1.5 millimeters, at the same time, it keeps the computational cost very low, which is ideal for a medical imaging system. And obviously, just to reiterate that this is the method that gives the better lateral separation between the two reflectors, 1.5 millimeters. And just to conclude on this work, so presented two novel algorithms. One is for the crosstalk suppression, and enabling us to detect reflectors as close as 7 millimeters away from the array. The second one is to effectively propose an image reconstruction algorithm that takes into account the intricacies of a narrow field of view array, and at the same time being able to extend the conventional detection rate. And I think, again, the main point that we want to stress out from this work is that narrow field of view pMUT arrays can be used very effectively for medical imaging applications, from diagnostics to industrial applications. I'd like to thank A-STAR and the Lab in Fab grant for supporting this work. Thank you very much, and I'm happy to take any questions.